we go. All right, we'll kind of record from this point so it's a little bit easier on you guys. So why available pressure is important. So number one, it's going to use to select our sprinkler head starting point for design. And it's also going to determine sprinkler performance characteristics. So the sprinkler on the left and the sprinkler on the right, what's the difference between those two?
Pressure.
Pressure, right? Which one would you rather have?
The one on the right.
Probably the one on the right, because the one on the left is almost too much pressure. So the water is pushing out so fast that it's just being misted and wasted out, while the one on the right is basically right, because again, our large droplets and it's going to fall to the ground, kind of even going into. You guys are studying with Hort Chem, we don't want to have too much pressure on our nozzles because then we equate the drift. Same thing with irrigation, we don't want to have drift. It's not going to harm anything if it drifts, but it's just wasted water. So pressure is important for these characteristics because it's going to determine what type of heads we can use. Either we could have, if we have a lot of available pressure, then we could then do pressure reducers to actually use these smaller heads, or we could put larger heads on there to use that available pressure. So the design capacity is determined in part by the characteristics of our project. So whatever we were going to design is going to equate from our project. So it's going to be determined by 3 particular methods, or in this case scenarios, depending on our site. So we could have either a metered municipal system, which is kind of that picture I posted up earlier with the house on the hill, that we're going to be tying off a municipal water system. We could have an undeveloped site, so we could basically build our flow. And site where flow path and restrictions are unknown, which we have to do a flow test. So here's that metered situation, definitions for the metered situation. So again, we have our point of C, where we're going to be tying in our irrigation system, where we're going to be building that from. Our delivery line is the line between our water meter and our point of connection. Our service line is going to tie our water source to our meter, and then the city water main, the municipal water line, bringing water to our project. So all of these are going to have already basically limitations built into them from the start, because the water source is only so big. The service line to our meter is going to be only so big. Our water meter is going to be a specific size. Our delivery line is also going to be a specific size. So all these are going to kind of restrict us down to some point to what we have at our point of connection, or POC. So you want to be calculating design capacity and available pressure. So scenario number 1 is that metered municipal system. So that's, like I said, our service is already in place and it's going to our residence or our commercial facility. So what we have there is just what we have. So our point of connection will be either at existing water meter or our delivery line. So there again, that point of connection. So this, our point of connection is past our delivery line, or it's attached to our delivery line. So restrictions on the supply are determined by the size of the existing water source. So remember, our existing water source, can you guys see my mouse pointer?
Yes.
Okay, so our existing water source, again, is our city water main in this example. Our limitation is starting from the bat, this city water source. So if the city water source is 40 PSI, that's what we're dealing with. If it's 60, that's what we got. So this is our start of our limitation. So scenario number 2 is no water service present. So the project is in planning stages. This would be, again, a new construction type of scenario, an agricultural setting, new development that you're, again, there's somebody contracted out that's building a whole ton of houses. So we need to determine what our water need is first to be before we start doing design capacity. That's our first step in scenario 2. And then scenario 3 is the irrigation system is to be connected to an existing water service or well. This becomes a little bit more complicated because then we have to calculate potential flow as well as pressure losses from our source to our point of connection. We also have to have a site flow test because, again, this will be based on our capacity, because our pond is going to be only so big because our pond's already in place, or how much water we could draw out of that well's in place. So we have to do all those calculations to what we have available, to what we can use before we even get into pressures. Did I lose anybody yet?
Not yet.
All right. So just some concepts that we got to know. First one is going to be design capacity. Second one is going to be dynamic pressure at our design capacity. Our third one is estimated dynamic pressure at our worst case head. So these are 3 pieces of information. This is kind of where we're going to get into those worksheets. So design capacity. Design capacity is our maximum flow in gallons per minute available for use by the irrigation system itself. How much water is going to be flowing per minute to be used up by that system. The dynamic pressure at our design capacity is going to be calculated dynamic pressure at our max possible flow. So whatever we can get out of the maximum is what we're going to be calculating this at. And then the estimated dynamic pressure is going to be at our worst case scenario head. So our calculated dynamic pressure at our highest head in our system. So we got to plan out, if we're just, let's say, adding a zone to an existing section, but that last head on that one zone we're adding is another 10 feet up above from where we're connecting it, we're going to have to factor that in, because with kind of going through that dynamic pressure, we have pressure loss as we go up in elevation. How much pressure loss do we have per foot of elevation? Should be 0.433 PSI, kind of going back to those given. Yep, so 0.433 PSI loss for every foot of elevation. So for every 2.31 feet, we're going to lose 1 PSI. So if we have to go up something like 50 feet, we could have a lot of loss to that worst case head. And if we only have 20 PSI to start with, we may not have anything at that highest point. That's why this is important. So determining design capacity. So we're going to do everything based on our metered municipal system, because that's kind of the easiest thing to calculate, because it's a given. It's what we already know. So our water delivery system and meter are going to be in place. We're also going to have a city water main, which is going to bring water to our project or the site, and it's going to be typically connected to that meter through that service type line. Our service line is the section of piping connecting our larger municipal supply to our water meter. And then the delivery line is going to run from our meter connection to our point of connection, which is then going to go out to our irrigation system. Then our POC, or point of connection, is where the irrigation system is connected to our water supply. So the water main brings the water to our kind of like our site. Our service line is going to connect that to our meter. Then the delivery line is going to take that from our meter to our point of connection, and then our point of connection is going to go out to our irrigation start. All right, so determining design capacity, our metered municipal system. So we have that first pipe, so that's our water source. So our city main, let's say it's going to be 80 PSI. Our second one is going to be our service line. So we're taking it from our water source, which is the city main, to our meter. That's going to be 1-inch type K copper pipe, 25 feet long. We're going to have a 1-inch water meter. an 1.25" schedule 40 PVC delivery line that's going to be 65 feet long, and then our point of connection. All right, finally, the one on the top is our worst case head. So we're going to have probably irrigation all the way up to here, and this is, again, exaggerated just because it's so steep. No one's going to put irrigation on the hill like that, but just if this was really drawn out, this is our worst case head. So our worst case head is 10 feet above our point of connection. All right, and kind of take note also that we're going up from our water source by 5 feet to the start of our meter, and then from our meter, we're going another 12 feet to our point of connection. So all these are going to mean something. So when we start doing design capacity, we need to gather site information first. The first part of this gathering is going to be elevation change. What type of elevation changes do we have? And that's going to be from our water source to our meter to our point of connection all the way to our worst case scenario head. We need to record and know all those elevation changes. We also need to record the static pressure at our main, because that's the pressure we're going to be basically sizing everything to. Our water meter size is going to play a large role because we can only push so much water through different size water meters. If we have a 1/2-inch diameter water meter, we can't really fit that much water through a 1/2-inch hole. If we had a 3-inch water meter, we could fit a lot more water through that. Then our service and delivery line length, size, and type, kind of going back to the charts last week, how we saw the friction loss characteristics. All those delivery line size, different size pipe is going to equate to pressure loss. The type of pipe is going to create or equate to pressure loss, and the length of that pipe is going to equate to some sort of pressure loss. All right, so now's the time. If you were in class, I would hand these to you, but we kind of can't. So if you guys can pull up, let me see if we just switch. I'll kind of bounce back and forth. If you guys can open this as a separate window, again, use a separate sheet of paper. If you did print them out, I would start kind of pulling them out right now. That we could start recording through these. And I'm going to take you step by step how we fill these out. So does everybody have these open or available?
Yes.
All right, sweet. All right, let's go back to the PowerPoint. So it'll be pretty easy to follow along with the first, my first group of slides. Again, if you guys have any questions, if something does not make sense, yell out and I can explain it a little better, hopefully. So we have this. So we have our piece of information. So our first step is to what? Gather our site information. So take note of our water source, what it is in pressure, 1-inch type K copper, how long that is, our water meter, our delivery line, and then finally that worst case head. So still kind of keeping everything in. So we want to gather our site data first. So looking at that sheet, we're going to be looking at line 1. Line 1 says static pressure at our source or main. That's what we're going to obtain from the purveyor, and usually the municipality department or wherever installed that water main will be able to give us pressure, that static pressure at that point. All right, so our static pressure at that point is 80 PSI. We want to write down 80 PSI in that kind of space. That's what we're going to have to work with. All right, so line 2 is our net elevation change. So that's going to be our change from our point of connection to our source, or a source from our point of connection. So in this case, we are going up how much?
17 feet.
17 feet. So it does say, kind of in quotes or in parentheses, it's going to say plus for uphill and minus for downhill. Why is that important?
Plus 17.
So it's plus 17. Why? It's important to the fact that we're going to have pressure loss or pressure gain. If we go uphill, is it going to have a negative effect on pressure or a positive effect on pressure?
Negative effect.
A negative effect. So the reasoning for plus is just to kind of equate to you guys that we're going uphill. So 5 feet plus 12 feet, Dylan said it, 17 feet. So we're going to record plus 17 in number 2. So now we need to calculate our PSI change due to elevation. And luckily this gives it to us. So we're going to take line 2, which is 17. And we're going to multiply that by 0.433. So you should get 7.36 PSI. So number 4, again, kind of looking at the bottom of this, number 4 is our static pressure at our point of connection. So what do we have at our point of connection to when we start putting irrigation onto this? Is going to be 80 minus 7.36 because we are going uphill, so it's a negative number. So we should have 72.64 PSI available to us at our point of connection, and that's static pressure, not dynamic. Have I lost anybody yet?
Not yet.
All right. So that's the first 4 lines of that sheet. So now we have this section, all right? So this is going to be where we're going to input all of our data from what we took off that main page. So it's going to have our service line, delivery line, water meter, gate valves, and other. So here's our site again. So our service line from the water purveyor is going to be 25 feet of 1-inch type K copper. Our delivery line from our site inspection is going to be 65 feet of 1.25 inch Schedule 40 PVC pipe. So on the first line, on number 5, you're going to write number or length should be 25 feet. Size is 1 inch, and the type of pipe is going to be type K copper. Same thing with our delivery line, 65 feet for our length, 1.25 inch for our size, and type is going to be Schedule 40 PVC. Our water meter, which we're going to also obtain from the water purveyor who installed that, is going to be 1 inch. So we don't need to worry about, there's no length and there's no type. We know it's a water meter, so all we have to do is record the size, which would be 1 inch. Now, if we had any gate valves or other, we would put those recordings in as well. But since we do not, make it a little easier. We don't have any isolation valves and we don't have any other. So just write none or 0 in those lines. That way it kind of references to you guys that there's nothing there. So this is what you should have. So in section, so our number and length, 25 and 65, none. Our size, so our service line is a 1 inch, our delivery line is 1.25 inch, and our water meter is 1 inch. So type K copper and Schedule 40 PVC. You guys are good on that part?
Yep.
All right. So now we got to go to our Rainbird books. About page 27. I think that was an older book. We're going to need to know our static water pressure, our water meter size, our service line length, and the type of service line pipe, because that's what those charts are going to give. So to determine the size of our water meter, we can even find that from our municipal office. We could look at the lid of the water meter, or it will be stamped on the meter itself next to our dials. And that's going to be a huge factor when determining flow. So those typical sizes can be 5/8, 3/4, 1 inch, 1.5 inches, or 2 inches. And we're going to refer to the pressure loss charts for our meter. So our service line is also important to determine the type, our diameter and length, because again, that kind of goes to those pressure loss charts. And we're going to be around page 103 of the Rainbird manual for the service line size estimation. We could also wrap a string around our pipe if we could expose it, and then we could also measure the length of that pipe. So lines 8 through 9 are our isolation valve lines. So either if it's a ball type or a gate valve or a globe valve, when we kind of talked about different types of valves. But since we don't have to worry about those, we'll just put none, but each one's going to have some sort of flow limiting characteristics to it. And then line 9, the other line, are any other components in the system. So it could be a backflow prevention device or even just some fittings. But for this, just as it's going to really confuse you guys adding all that stuff in. So for right now, we'll just say none. So lines 10 through 12. So think of these values as our rules to follow. So the first one, so estimates from line 10 and 11 and 12 will be compared to each other. And those lowest value of the 3 lines will be determined which flow rate to use to estimate our design capacity. So the first 3 lines are going to be what we're gathering our data. And out of those 3, we're going to use the lowest one. So let's say if we have a 40 gallons per minute, a 35 gallons per minute, and a 10 gallons per minute, we're going to base our restrictions on the 10 gallons per minute because that's our lowest one. We can't exceed that lowest value. Does that kind of make sense why we can't exceed that? You guys are quiet. I feel like I lost you.
No, I'm here.
Okay.
I am. I don't know everybody else is.
All right, so let's get into it. So you guys are gonna need your books, your Rainbird books, and also this sheet. So pressure loss through our water meter is not to exceed 10% of the available PSI at source line 1. Right? Volume through the water meter is not to exceed 75% of maximum safe flow of the meter. The velocity through our service line is not to exceed 7.5 feet per second. And that's our main to our meter. Right? Now we're going to talk about what those mean. So rule number 1, or basically number 10 on the sheet. Pressure loss through the water meter should not exceed 10% of available PSI at our source. And we're talking about static pressure, which is, it kind of has in parentheses line 1. So we're looking at line 1, and we've all recorded line 1 to being what?
80 psi.
Static pressure at main.
Yeah, 80 PSI. So we take 10% of 80 PSI and we get 8, right? So 0.10 times 80 is going to give us 8 PSI allowable loss. So that's how much we can lose out of that. So go to page 106 in our Rainbird books. Everybody get to that page?
Yep. 1 inch meter.
So we look at our 1 inch meter because that's what meter we have. So we see all those numbers kind of along the side. It goes from 0.01 to all the way to 15.0. Everybody see that?
Yep.
So looking at 8, so we don't want to go over 8 PSI loss. So we basically want to go to the next closest number. So we kind of go down 7.8 is not above 8 PSI loss. So that would then equate to 36 gallons per minute would be our highest flow rate that does not exceed 8 gallons per minute. Does everybody see where we got 36 from?
Yes.
Let me see if I can pull up.
Yeah.
Let's go with this. All right, just so you guys see, page 106. That's the one. Page 106 of my book.
I think you have to go back one from where you started.
They go too far. Nope, should be right.
Oh.
Down way too far. Give me a second. There we go. So pressure loss through our meters. So right here is our 1-inch meter. We don't want to exceed 8. So that means we have to be at 7.8 because that's the one closest before we exceed 8, because the next one over is going to basically jump to 8.7. So at 7.8, we should have 36. All right, so that would be our first one. So we would write 36 gallons per minute in that first line. So this is basically designed to not overtax the municipal water, the water meter, because if you overtax it, then it will fail and then we'll have problems. So rule number 2, volume through our water meter should not exceed 75% maximum safe flow of the meter. So we can still go back to that 1-inch water meter. So we're still on that same page 106. So the maximum flow through a 1-inch water meter is 50 gallons per minute. So kind of jumping back here, I get this to share. So how we came up with that 50 is if we go to a 1-inch meter, at the bottom of this chart, as much as we could push through this meter is 50 gallons per minute. However, we don't want to exceed, we have to be at 75% of that safe flow. So we would take that 50 gallons per minute, multiply that by 0.75 to give us 37.5 gallons per minute that we can push through that meter safely. Does everybody see where I got that number from?
So that was, oh, just a 75 and 50. Okay. Yeah.
Yep, so it's basically that 50 gallons per minute because that's as much as that will. Because that's our pressure loss, because at our pressure loss at 50, we're at 15 PSI loss. So there is no other markings for if we go to 52 gallons per minute because that meter safely cannot handle that. So to be, we're going to 75% of that gallons per minute, giving us 37.5. So we should have 37.5 gallons per minute in that next line. Now our third rule and third line, our velocity of the flow through our service line should not exceed 5. And I also have in parentheses 7.5 feet per second. So if we kind of, what material is our service line? Let me ask you guys that. So our material for our service line was that type K copper. So if you guys, I would go to type K copper water tube. In my book, I'm at page 102. It should say type K copper water tube. So notice, if I kind of go back here, we go back, let's go find type K copper water. So we don't want to exceed, ideally, from what this actually sheet says, is 7.5 feet per second, but really we could almost even dial that back more to 5 feet per second. So notice again the gray section of this chart. Anytime we're exceeding 5 feet per second, we start going into the gray, right? So it's saying we can do it, but it's going to be a little bit more taxing on the system. So if we're designing for the most longevity, then we would want to stay within 5 feet per second. So kind of let's use 3/4 inch type K copper for an example. Only safely put 6 gallons per minute through that without exceeding 5 feet per second in flow. So with this chart, we can kind of get away, and we're going to get away with 7.5 feet per second. We don't want to exceed 7.5 feet per second, then we're looking here. So we could get 7.35, but the next flow, 11, brings us to 8.08 feet per second. So this would be our maximum flow through this pipe without pushing past 7.5 feet per second. Does that make sense on you guys? So that velocity should not exceed 7.5 feet per second. So we have a sample problem. Our service line is 1 inch type K copper. So we go to those charts. So let's go back. All right, so at 1 inch type K copper, what flow amount is still below 7.5 feet per second without going over that number?
14 gallons per minute.
How much?
14.
So a 1 inch pipe, you're saying 14, without going over 7.5 feet per second.
It's got
Does anybody
6.5.
What are you saying, Dylan?
It's 6.57.
But you don't want to go over 7.5. So is there a number higher than that? Because remember, we'd stay within the gray. We don't want to exceed 7.5 feet per second.
Oh, is it under the velocity column?
Yes.
Yes. Okay.
There you go.
Yeah.
All right.
So 7.4. So 18.
There you go. 18 gallons per minute is the maximum safe flow through that meter without going past that 7.5 feet per second. I can see where you got lost. So we're not looking at this column for this instance, but we're looking at that velocity column.
Okay.
So the velocity can't exceed 7.5 FPS. So that gives us an available flow of 18 gallons per minute. Does anybody have any questions how Dylan came up with that?
No.
Nope. Let's go back to our problem. So if we were looking at 5 feet per second, we would actually have a safe flow of 12 gallons per minute. But since we're looking at 7.5, we could have a safe flow of 18 gallons per minute. So we're going to write 18 gallons per minute on that third line. So line 10 should read 36 gallons per minute. Line 11 should read 37.5 gallons per minute. And line 12 is equal to 18 gallons per minute. So our design capacity is our lowest GPM of the 3 flows. So that's going to include lines 10 through 12. So our lowest flow through all 3 of those is number 12. So that's what we're basing all of this information on, because that's as much flow as we could possibly have through our entire system because of that limiting factor of our service line. So our meter is not restricting us. Our velocity of the meter is not restricting us, but our service line is restricting us. So if we made a bigger service line, we could get more flow. So line 13 should have 18 gallons per minute. And there's that kind of written out. So 36, 37.5, and 18. So our design capacity is 18. So lines 14 through 19 now are our dynamic pressure loss calculations. So we have to establish our flow rate. So in our example, we have 18 gallons per minute because that is our max. So now we need to use that to design our system to our point of connection. So we're going to have our losses in between our service line, our delivery line, water meter, right? If we had an isolation valve or any other components, we would also have pressure losses through those as well. So we're using the information that we have from lines 5 through 9 to now work into lines 14 through basically 18. So here's lines 14 through 18. So our pressure loss through our service line per 100 feet, our delivery line, our water meter, our isolation valves, and then other pressure losses. So let's start putting in the information. So our first one, we know our flow is 18 gallons per minute because that's our restricted capacity. That's all we can work with. The type of line is type K copper. So we're going to take that pressure. So if we kind of go back to our type K copper chart, kind of jump back. So we're at our type K copper. We know that it's 1 inch. Our flow is 18 gallons per minute. So this is our pressure loss, is 10.47 PSI. So we want to keep that number, that 10.47 PSI. And we want to insert it into this equation here. So our service line, so 10.47 PSI, I would write 10.47 PSI here. And we're going to write the length of that pipe. So we know it's 25 feet. So we're going to take that 10.47 PSI, multiply it by 0.25, because that's what's our 25 divided by 100 is going to give us 0.25, because that's the feet. So 10.47 times 0.25 should give us how much? So 10.47 multiplied by 0.25 should give us 2.62 PSI loss. So between that section of line, we're going to be losing 2.62 PSI. So we're going to write 2.62 PSI on that next line right across from it. Now we need to figure out our pressure loss through our delivery line. So our delivery line is what material?
It is Schedule 40.
Yep, Schedule 40 PVC. So again, we're basing on that 18 gallons per minute. The type of line is Schedule 40. Let's go back to our chart. Let's go back. We got to go up to Schedule 40. So we should say Schedule 40 IPS. Here it is. So Schedule 40. It's an 1.25 inch line. We have 18 gallons per minute to work with. So kind of going over, you would have a pressure loss of 1.88 per 100 feet. So we're going to input that into our chart. So that 1.88 PSI per 100 feet, we have 65 feet. So we're going to take 1.88, multiply that by 0.65, and that should give us 1.22 PSI. Everybody see how I came up with that one?
Yep.
All right. And now our water meter. So our flow, same thing, 18 gallons per minute. So we're going to go to our Rainbird charts. We're going to find our water meter. I don't go too far. So here's our pressure loss through our water meter. We know it's a 1-inch water meter because we recorded 1 inch. Our flow is 18 gallons per minute because that's our limiting factor. So we should have 1.8 PSI loss through that meter. So we should record 1.8 in this chart. Again, water meter, we should write 1.8. 1-inch meter, PSI loss, 1.8 PSI.
Right.
Now we have to take all of our losses because each one's going to have pressure loss. So we have 2.62, 1.22, 1.80. So we have a total loss from our main or city water main to our point of connection of 5.64 PSI. So we want to write 5.64 PSI on line 19. So now line 20 is going to ask us the static pressure at our point of connection, and we already did that because that's basically line number 4. We're gonna take line number 4 and edit, or just basically write it on line 20. So we're gonna have 72.64 PSI, and then we're gonna take line 21, which is what we just calculated on line 19, which is going to be 5.64 PSI, and then do that math. So 72.64 PSI, which is what our pressure is at our connection, our static pressure. And then we're going to subtract that from our dynamic pressure calculations. Should get 67 PSI. That should be line 20, line 21, and line 22. So we have 67 PSI of available dynamic pressure at our POC. So now how much pressure is available for our sprinkler operation? So we have up to this point, 67 PSI. So we've lost from basically our source of 80, we're now down to 67. However, we still need to get up to this worst case scenario head because this is the head that's going to be at our highest elevation, which is going to have the most possible system loss. So we must know the PSI to select our sprinklers. So we're going to kind of estimate our pressure at our worst case scenario head. So the steps that we're going to kind of take is the estimating of the amount of pressure lost between our point of connection and the highest head. We're going to subtract that PSI loss from the dynamic pressure at our POC. So we're going to subtract that pressure lost from that 67 PSI. And then from there, we're going to add or subtract our PSI lost or gained from our elevation. So that elevation is now going to play a factor. So kind of remember how we talked about that 1/3 kind of rule? That we're always going to have 1/3 loss through components. So we need to factor in that 1/3 loss from all of our connections, now from our point of connection to that worst case scenario head. We're going to have, again, swing joints. There's going to be couplers. There's going to be 90s. There could be T's. We don't know how much in to kind of, instead of doing each individual part, which we could, which would be a lot of math, we're just going to basically factor in 1/3 is gone. So We're going to have 2/3 of the available pressure still left at our point of connection. So we're going to take that 67 and multiply that by those 2/3, which is 0.67. So at our worst case head, we have 44.89 PSI. So line 23 should be reading 44.89 PSI. So now we have to look at elevation change. So our elevation change is going to either increase that pressure or decrease that pressure. So we have to determine that elevation change from our point of connection to that worst case scenario head, which happens to be the highest one. So we're going to add, we're going to do a plus if uphill, minus if downhill, just like we kind of did with line number 3. So we're going to take that 0.433 PSI, because that's how much pressure we can either gain or lose depending per foot. Then we're going to take line 25, which is the subtraction of line 24, which is that pressure change through to elevation to that head. So you should have, we're going uphill 10 feet, because that was, let's kind of jump back. So our worst case scenario head is 10 feet above. So we would take 10 multiply by 0.433, because that's how much pressure we're going to lose per foot. So we should be losing 4.33 PSI.
Yeah.
Have I lost anybody yet?
Negative.
Negative.
No.
All right, good. All right. So here's a pressure gauge. Does everybody know how to read a pressure gauge? Has everybody seen it before? So we know what our pressure was. So if we hook this pressure gauge up to our main, we should have been at 80 PSI. So however, we're at 67 PSI. So 67 PSI is what our dynamic pressure was at our point of connection. So as soon as we plugged our pipe in, that's what we knew we were starting with to now design our system or build our system out off of that. So we have 67 PSI to work with. However, we needed to get that head up on that hill because we needed to irrigate that area. We had a green up or we had some trees or some shrubs or a flower bed that we needed to irrigate that was up on this bluff. So that's what we have to do. So we have 22.11 PSI or 22.11 PSI set aside for pressure losses from our point of connection to that worst case head. So we had that, we lost that 22.11 PSI due to the fact of those components in that system. Again, the piping, the connections, any valves, we lost, again, a whole 1/3 of our pressure. So now we're down to that 44.89 PSI. Then we also had that elevation change, right? Because we're going 10 feet higher from our point of connection. So now we're down even further. We lost an additional 4.33 PSI. So now that our estimated PSI for our worst case sprinkler is going to be 40.56 PSI. So that's how much pressure we can work with to operate that head. Have I lost anybody on this sheet?
Nope.
Everybody good?
Yep.
Speak now or forever hold your peace. All right, so that would be our first sheet. So there's that kind of lines 22, 23, 24, and 25. How I kind of came up with that and what our available pressure is.
Just so much for one number.
It's a lot of work, but luckily it kind of spells out the steps we have to take. We have to do a little bit of memorization kind of in that middle section. Again, those determining factors are what we kind of have to know to start grasping our numbers. But if we know where to get those from, it's fairly easy. It's kind of, again, simple math. But you have a lot of numbers because there's a lot of information and a lot of factors that do play in to the pressure. So we started out with 80 PSI. And at that worst case head, we cut that number basically in half. So we only have 40 PSI. So a little bit of distance can equate to a loss. All right. So this is the first practice problem I want you guys to kind of do, and I'll kind of do this together with you guys. So I want you to kind of take down all this information. So I'll kind of start with line 1. So line 1 is going to be the static pressure at our source. So what's our static pressure at our source?
60 PSI.
60 PSI. All right. We also need to write in all those materials. We'll kind of go to line number 2. We'll kind of wait on that stuff. So we have a net elevation change. So what's our net elevation change? And that's from our source to the point of connection.
13 feet.
So 13 feet. So we'll plug 13 feet into that. And we know it's a positive because we're heading up. Right. So then our PSI change due to elevation is going to be line number 2, which is 13 feet multiplied by 0.433 PSI. Should give us what?
5.63.
Yep, actually, I think I got 5.62.
It's like 629, but
Yeah. So 5.63 PSI. And then our static pressure at our point of connection. So is line 1 minus basically line number 3 should be what?
$54.37.
So 54.37 PSI. Has everybody kind of got what Dylan got? Is anybody confused at this yet?
Is anybody alive?
Is anybody alive? Only Dylan here. Mike and Karina are muted. Harmony.
Oh, jeez.
All right. So now lines 5, 6, 7, 8, and 9. So this is where we're going to put in our information. So our service line should be 20 feet. All right. So we'd write 20 feet in the number or length. And we would write 3/4, which is the size. And then the type is type K copper. Our next line, delivery line, which is going to be right here, is a 3/4 inch. So that's our size. It's going to be schedule 40 PVC, which is our type. And then it's 400 feet long. So this distance from our meter to our POC is 400 feet. This one from our water source to our meter is 20 feet. Then finally, our meter is 3/4 inch in diameter. All right, and we can even write 12 feet if we need to just kind of record that. And we could put that again on the top of the sheet just so we know that's our worst case head. Then our gate valve or other, there is none, so we could just put none and none. So now we need to look at the determination of the design capacity. So let me kind of jump to our sheet. I can see how good I am at writing something here. So we should be able to kind of, that's not really going to work. Let me just draw. All right, so the service line should be 20. Our size, 3, oh my goodness, 3/4. And the type is copper. And this one's going to be 400 feet And that one's also going to be 3/4. So record our values here. So pressure loss through the water meter is not to exceed 10% of the available PSI at our source. So what's the available PSI at our source?
60 psi.
60 PSI, because that's our base number. So what's 10% of 60?
6.
6 PSI. So we can't exceed that 6 PSI. We want to go to our chart. So if we can't exceed 6 PSI of loss, we know our water meter is 3 or 3/4 inch. We can go up to 6, but we can't exceed 6. So 19 gallons per minute,
5.8.
5.8. And if we went up to 20 gallons per minute, we would go to 6.5. So 20 gallons per minute exceeds 6. So that means we're at 5.8. That's our biggest number we could go. So our gallons per minute in this instance should be what?
19.
19. All right, so 19 is the max we could push through this. So we'd write 19 on that gallons per minute section. So our next line is volume through the water meter. So we cannot exceed 75% of the maximal safe flow of that meter. So that maximum safe flow of this meter is what?
30 gallons per minute.
30 gallons per minute. Does everybody see how Dylan got that?
Just assume. Just assume I did.
Yeah, what's that, Dylan?
So just assume.
Yeah,
Got it.
I'm assuming.
Yeah.
So, because again, this number doesn't exceed down, so we have 30. So we take 30 and multiply that by 0.75 to get 75% of the safe flow.
So 22 and a half.
Yep, 22.5 gallons per minute. So we should have 18, or actually, nope, 19 gallons per minute. And we should also have 22.5. Now our velocity should not exceed 7.5 feet per second, and that's our water main. So what's our water main made out of?
Type K.
Type K copper. Right? So that size of that water main is 3/4 inch. So we cannot exceed 7.5 feet per second of that sized pipe. So what number would that be?
I'm in the millimeters section. 1 second. There we go.
Anybody could beat Dylan to it. I'll be happy. Dimitri, what'd you say?
10,
10.
3/4.
Yes, 10. So everybody see 10. So if we look at velocity feet per second of a 3/4 inch type K water tube, we'll go down. Oops, sorry, so 7.5 feet per second. If we go to 11, it's 8.08 feet per second. Too much. We can only be at 7.5 max. So 10 gallons per minute is our max flow through this type of water tube. So on line 12, we would write 10. So kind of jumping back to here, I could write 10 right here. Let's see. That'd be sweet if I write 10. Oh my goodness. So I'd write 10. I wonder. That doesn't work. So we would have 10 here. So we should have 19, 22.5, and 10. So our design capacity is our lowest of the three. So what number would that be?
And
10 gallons per minute. So that's going to be our number we're going to base everything on. So now we have to do basically our pressure loss through each of these. So we know our service line is type K copper, and we're dealing with 10. So we go look at our charts. At our 3/4 inch, we have 10 gallons per minute. So the pressure loss should be 14.41 PSI per 100 feet. We would plug that, so 14.41 PSI into here. Our length is 20 feet, so we'd be taking 14.41 and multiplying it by 0.20. And that should give us how much pressure loss?
2.88 PSI.
2.88 PSI. So we would write 2.88 PSI in this section. So now our delivery line is going to be 3/4 inch schedule 40 PVC. So go back to our charts. We'll find schedule 40 PVC. All right. The size is 3/4 inch. We know we have a flow of how much?
10.
10. Yep, Dimitri got 10 gallons per minute because that's our most maximum.
It's our lowest.
That's our lowest. So at 10, we should have,
Losing 7.77.
yep, 7.77 PSI loss per 100 feet. So that should be a big one. So how many feet of pipe do we have?
Isn't it like, what is it? 65 foot.
How many feet?
Is it 65?
It should be
Was I right?
400.
Oh, I wrote down the wrong number.
So 400 feet.
400.
So let me go back
Look
to
at
the. So here's our example. So we have 400 feet of 3/4 inch schedule 40. So we're basically taking that 7.77 and multiplying that by 4. So what's our pressure loss through that section of pipe?
31.
31.08.
31.08 PSI. So there's 31.08 PSI down the window. And then we're going to take our water meter. So going back to our charts, we'll find the water meter.
What page is the water meter on? Is it in the back?
Yep, it should be page, what's this one? It's a gate valve. So on the line, yeah, page 106. So
Oh, okay.
6, according to this. So again, we're basing it off 10 gallons per minute because that's the max flow we can use. 3/4 inch. So we have a flow of, or a pressure loss of what?
1.6.
1.6. So input 1.6 into our chart water meter right here, line 16. Isolation valves and other are 0 because we don't have any, so we could just write 0 and 0. So we should have a total loss, so lines 14 through 18 should have a total loss of 35.56 PSI. Did everybody get that?
What line was that?
Line 19
Oh, okay.
should be 35.56 PSI. So our line 20 is going to be static pressure. So line number 4 above, what was line number 4?
Did I not write it down?
Line number 4 was our static pressure at our POC. So our static pressure at our POC is 54.38 PSI. So line 21 is actually just moving line 19 down to that line. So line 21 should be, again, 35.56 PSI. So line 22 is basically taking the static pressure at our POC and subtracting it from our pressure loss to our source or to our POC. So it's 54.38 minus 35.56 should give us 18.82 PSI. So this should be 18.32 PSI. Make sense?
Yeah.
Okay. So then we need to do basically our friction loss calculation. So everything from our point of connection to our worst case head with all the fittings and everything, we're going to basically lose a third. So we have 2/3 left. That's what we're going to calculate on. So we're going to basically take, or we are going to take our 18.82 PSI, and we're going to subtract that or multiply that by 0.67. So that's going to give us what?
Was it 18.32 or 82?
82. 18.82.
82. Uh, 12.6.
Yes, this is 12.6. We have 12.6 PSI now to our head. So now we also now have to take elevation into account. So kind of going back to our picture or our problem, we have 12 foot of rise from our point of connection to our highest head on the hill. So we need to use that 12 feet, kind of going back to our chart. So we're going to have plus 12 because we're going uphill, multiply by 0.433 PSI because we have 0.433 PSI loss per foot. And that's going to give us
0.866.
how much?
0.866.
12 times
5.19.
5.19. That's what I got. 5 or
So
0.20 rounded.
So it was 12 times 0.43. Oh, yeah, it is. Okay. I must have the
Okay.
wrong one. Yeah,
No
5.19.
problem. So we have 5.2. Is that a pressure gain or a pressure loss?
Loss.
It's going up,
Loss.
uphill.
So it might help too to just put minus 5.2. So our pressure now available for that sprinkler to operate is how much?
I'm sorry, say that again.
So that bottom one, pressure available for the sprinkler to operate is how much pressure?
I'm sorry, it was 18.83
So we had 18.83.
minus 5.2,
We forgot-
13.63,
How much?
13.63.
You forgot a step, Dimitri. Line 23 is the 2/3 estimate. So we want to put that 18.83 PSI and multiply that by 0.67 because we lost a third through our fittings. So 18.83
Oh, okay.
times 0.67,
And then minus the 5.2.
yep, is
So
12.62.
7.4161.
Yes. Wow. So that lost so much pressure.
Yeah, so at our head is only 7.4 PSI. So we started out with 60. And to get to that hill, all we're working with is 7.
That 400-foot line doesn't help.
What's that?
The 400-foot line doesn't help.
Exactly. And this kind of scenario really illustrates why it's important to know this. Because if, let's say I knew we have 60 PSI, good, we have 60 PSI to work with here. No, we don't, because of all of this. Because once we go through this, we lose a ton, plus getting to this point, you're gonna lose even more. So if we're designing a system or even adding on to a system, we're gonna have a known pressure, and we're gonna have to work off that pressure to see if it's even possible. All right, we're gonna do one more. Just to make sure you guys get this 100%. So step number 1 is our static pressure at our source. So our static pressure at our source is what?
70.
70 PSI. So now we need to know our net elevation change. So from our source to our point of connection, what's our change?
21.
0.3 or 31.
31, yeah.
So we have 31 of positive elevation change. So now we have to figure out our pressure loss because of that change of elevation. So we take 31 and multiply it by what?
0.433.
Yep, 0.433. So that should give us what number?
13.423.
Yep, 13.423, and kind of round that to the nearest hundredths place, 13.42 PSI. So now line number 4, our static pressure at our point of connection should be what?
Oh, it's just that. Okay, so 79. 56.58.
56.58. Perfect. So what Dylan did is he took our 70, which is our source at our main, and subtracted that elevation difference, pressure loss. So you take 70 minus the 13.42 PSI loss due to the gain in elevation, and we would have a base static pressure of 56.58 PSI. All right, so now, so you would write in this line 56.58 PSI. So now we have to input all of this information. What was that, Dylan?
No, it's just, yeah, you got to fill in everything.
Which this one's fairly easy. So our service line is 80 feet long, so we'd write 80 in our length. It's a 1-inch pipe, and it's type K copper material. Our delivery line, so from our meter to our point of connection, is going to be 50 feet long, 1.5 inches in diameter, and it's going to be made out of Schedule 40 PVC pipe. Our water meter is what size?
1 inch.
1 inch. And then our gate valves are other. None and none.
None and none.
So Zippo, Zilch, none of them. So don't need to worry about those guys. So now we need to figure out these things: the pressure, the volume, and our velocity. Let me delete that. Done.
We take 10%, so it's 10% of your static, which was 70, so it's 7, right?
Yep, so 7 PSI. So now we're going to go to our chart. So we can't exceed 7 PSI.
1 inch that we're going off. $34.
Yep, so 34 gallons per minute. So 7 PSI loss we cannot exceed. So 6.9 is our max. So 34 gallons per minute. On line 10, we would write 34 gallons per minute. Has everyone see how we came up with 34?
Yep.
All right, so now we got to find the volume. So our volume is not to exceed 75% of the maximum safe flow of that meter. So what's the maximum safe flow of that 1 inch water meter?
15. Or I'm sorry, 50. Excuse
50.
me.
So our gallons per minute is our flow. The 15 is our pressure loss. We cannot exceed 50 gallons per minute. But 75% of that is our safe flow. So we have to take 75% of that 50.
37 and a half.
So 37 and a half. We cannot exceed 37 and a half gallons per minute. So on line number 11, we would write 37.5 for our safe volume. Now our velocity, we cannot exceed that 7.5 feet per second. And that's from our what? Is that our service line or delivery line? Service line, right? So our service line is our city main to our meter. So we cannot exceed our service line. So now looking what our service line was, our service line was that type K copper, 1 inch. So we have to go now to type K copper, 1 inch. And we can't exceed 7.5 FPS.
So 18, excuse me, 18 gallons per minute.
1 inch. 18 gallons per minute. So our max is 18. So going back to this chart, we would write 18 on this. So what would be our lowest of the values?
18.
18. So now we got to do our dynamic pressure calculations. So our service line is that type K copper tube, and it's going to be how long?
It's 20 feet long. Or no, sorry,
80.
that's the wrong problem. It's 80 feet.
80 feet long. So we know we can only push 18 gallons per minute through it. So our pressure loss should be 10.47 PSI. We're going to take 10.47 and multiply that by 0.80. So what's our pressure loss through that section of pipe?
83.76. Or I hit the wrong number. Where is that?
Did you say 8.376 or 83.76?
83.
Shouldn't be 83. Did you multiply it by 80? 0.80?
So it's the 10 point. What was the number?
Should be 10.47
That's 0.8.
times 0.08 or 0.8, sorry.
0.4.
Yeah. 0.8, you're right.
0.3. Yep, there you go.
So it should be 8.38. All right. So that's our pressure loss through that service line. Now we need to figure out our delivery line. So what's our material over delivery line?
Schedule 40.
So schedule 40, so we want to go up. Schedule 40 pipe. We have a flow of how much? So we should have a flow of, again, 18 gallons per minute because that's our max capacity. So 18 gallons per minute. Our pipe is 1.5 inches in diameter. So our pressure loss is what?
0.89.
0.89 PSI per 100 feet. We're right 0.89 in where that pressure section is. I'm kind of going back. So 0.89 here, because that's our PSI loss. And then our length is 50 feet. So it'd be 0.50. So 0.89 times 0.50.
4, 5. Going around.
Yeah, so 0.45. That should be 0.45 PSI loss. And then finally, our water meter. So we'll have to go back to our charts, to our water meter. If we ever get there. So our flow is what?
18 gallons per minute.
18 gallons per minute. So our pressure loss through that 1-inch meter,
1.8.
1.8 PSI. So you would take now all those numbers and add them together. So we should have 8.38 plus 0.45 plus 1.8. So that should give us a total pressure loss of what?
Um, $3.14.
3.14. How'd you get 3.1?
I have to be missing 0.89, 0.45, and 1.8.
Sure, it's 0.89. Where'd you get the 0.89 from?
That was, oh no. Wrong.
So line 14 should be 8.38 psi.
Yep,
Line 15 should be 0.45 psi.
yep,
And line 16 should be 1.8 psi.
okay.
So if we add all those together, because we don't have any isolation valves and we don't have any other pressure loss, so we should have 10.63 psi. So
There we go,
line
yep.
19 should read 10.63 psi.
There we go.
Line 20 is the number on line number 4, which is,
56.58.
yep, 56.58. Line 21 should be what we just had, which is 10.63. So then we're taking 56.58 and subtracting that by 10.63.
45.95.
56. $45.95. Perfect. And now we have 45.95. So now we have to, that's our pressure at our point of connection with dynamic pressure. So we have 45.95 psi to work with to get to our worst case scenario head. So now at this point, we're going to put in our pipe and our fittings, all the stuff to get to that head to make that work. So we're going to lose 1/3 of that pressure. So we only have 2/3 of that pressure to work with. So we're going to take that number, which is 45.95, and we're going to multiply it by 0.67.
30.78.
Yep, 30.78 or 0.79 if you want to round up.
Yeah.
So it should be 30.79 psi on line 23. So that's our working pressure at that head. Right now we have also an elevation change. So our worst case scenario head happens to be 8 foot on top of this hill. So we're going to have a static pressure loss through to that 8 foot. So going back to our chart or this sheet, we're going to have an 8 foot of uphill. So plus 8, multiply that by 0.433. What number did you guys get?
What was the second section? Was it 12?
The elevation was 8 feet.
Oh, 8 feet, okay. 3.4 or 3.5.
Yep, well, yeah, 3.464. So 3.46. So we have 3.46 now. Is that a pressure loss or gain?
It's pressure lost.
Pressure loss because we're going uphill. So we're subtracting that from 30.79.
27.33.
27.33.
Yep.
So that is our available pressure at our worst case scenario head. So looking at this, we've gone from 70 PSI to 27.33 PSI at the top here. All right, does anyone want me to cover anything again?
Pretty easy.
Pretty easy. So once you figure out where to find the information, gathering the information isn't too bad. So just to recap, our critical first steps in irrigation system design is this design capacity. And it's going to determine the system's design capacity over what it can handle. Also available to dynamic pressure is required to, again, select the appropriate sprinklers. So we could either, with that, let's take that last number, for example, 27.32 PSI. Can we use a large rotor? Probably not. Can we use the mist head? Yeah, that'd be a good amount of pressure for that. And it's also going to let us equate to how many circuits do we need to divide everything up into. So once we divide everything up, then we could also size our valves, and we could also size the regular system components. Because honestly, if kind of looking at this, we have our point of connection. Do we need to use a 3-inch pipe to get up to that top of that head? No, because our delivery line's already been choked down, or it's already kind of choked to an 1.5-inch pipe. So why make a larger pipe if we don't have that flow already? So this kind of helps us size everything to start dividing everything into appropriate components. So before we select sprinklers, as a designer, or even as somebody looking at how this was built, we need to look at the flow available for each sprinkler use and what pressure can be expected at the sprinkler heads. So this last problem, I'm gonna put this presentation up. I'm gonna have the recorded version up on YouTube, which you guys, I'll give a link to, and then I'll also have this slide up that you guys can kind of click through to see the steps. But for your homework, or for the kind of the quiz this week, I want you guys to do this problem. So practice problem 3. So how I want you guys to kind of, I guess, get this to me is I'll kind of put up a quiz link up on Venko Hall, and I'm just gonna put it in essay format, and just I want you guys to break line by line down what your number you came up with. So if you guys
Do you want to do like a Dropbox or something, and just have us like drop our docs in, or do you want to do that?
I could, if you guys want to, I think it might be easier just to kind of,
We can just, I don't care. It doesn't matter to me.
I might set it up just for the essay thing and just kind of go, just write number 1, what your number was, number 2, and you'll just basically have 25 lines. And then, so that way, if you guys do happen to slip up in one part of this, you're still going to get credit because you showed your work and you kind of followed through with how you kind of progressed through. So this is your assignment this week. So does anybody have any questions on this before we kind of dismantle?
When is problem 3 due?
What's that, Carly?
When is problem 3 due?
I'll have it due, we'll have it due for, I guess the start of next class, so Wednesday or
Okay.
Thursday at 11 o'clock a.m., just like the last one was.
Okay.
And if you
Alright.
guys have any questions from now until then, please ask them. So it's a lot of information. You guys probably thought last week was a lot of stuff to take in. This week is also a lot of stuff to take in.
It's not that bad though. I mean, just taking it step by step. I mean, when it breaks it down, and it's like, all right, do this line by this line, and it's not that bad.
The information's basically all there.
Yeah.
And for your test
Read the
towards
charts.
the end of the semester, I will give you one of these, or you guys will have one of these. and you will have access to your chart. So it's just taking the charts and inputting it into the design sheet. To come out at the end with the number. But next class, we'll kind of talk about or go into selecting sprinklers, what we have to do to select sprinklers. We'll kind of even get into wiring, and we'll try to wrap all this stuff up because believe it or not, next week is our last week of actual, I guess, technical instruction, and then it's finals. So we may have to do a little bit of, or probably might do a little teaching in the beginning of finals week. Maybe that Monday we could set up a class just to kind of go over everything and maybe do a quick review and then kind of go from there.
Yeah.
So if you guys don't have any questions for me, enjoy the rest of your day. Or you guys got
Ben's Hort Chem test, right?
Ben's Hort
About
Chem
10
test.
minutes.
So in how long?
About 10 minutes.
All right. So you guys got a little time to kind of bulk up on that.
He's giving us a 3-hour window, so. Well,
Yeah, you guys will do fine.
yeah.
But again, if anything is confusing or even as you're kind of going through it, just feel free to send me an email and I could answer your questions.
Sounds good.
All right.
All right. Have a good day,
All right.
guys. Good luck.
Yep. Yeah, thank you, Ryan.
All right.
Have a good one.
See ya.
Have a good day, guys.